My presentation is viscoelastic and viscoplastic damage models for rate-dependent shear behavior of shales. It's a little bit changed in the title from the abstract that I've said. Okay, what are the motivations for my presentation? Number one is that shales are the most common material on the surface Earth. Okay, it's found everywhere. In fact, it's widely encountered in many geoenergy and geoenvironmental applications. At the same time, shales are very challenging materials. They exhibit very complicated behaviors, very multifaceted behavior. Two of the important issues in the understanding of mechanical behavior of shales are the loading rate dependency of the stress-strain response and modeling of stress-strain response that spans the pre-peak, failure, and post-failure regions. So these are the focus of my presentation. And to address these challenges in understanding, I will be presenting two models: a viscoelastic damage model, which is really very simple, and a viscoplastic damage model. And you'll see why there are two models that are being presented. So for model one, let me present first the results of triaxial tests that were conducted on a shale from China, which is found in Chongqing. It's a lower Silurian shale. Based on mineralogy, 73% of the mineral content are brittle, so it's expected to be very brittle materials. The main component, 55.51% by weight, is quartz, which is a very brittle material. The samples were drilled horizontally in the field, so which means that the bedding planes are vertical in the sample, and they will be parallel to the sigma sub 1, sigma sub 1 being the vertical stress, the major principal stress. Here's the result of undrained shearing under constant confining pressure of 50 megapascal at different axial strain rates. Note that we have to do undrained shearing because it's impossible to do drain shearing in shales because of their very low permeability. And at the same time, in this set of testing, pore pressures were not measured, so we'll be talking in terms of total stresses. So as you can see, in general, there is an initial compression stage during the loading. This is, by the way, the axial strain versus the diatoric stress, sigma 1 minus sigma 3, or shear stress. So again, initially, there is an initial compression. This initial compression is due to reloading, closure of the micro cracks that were opened during the sampling, during the drilling in the sample. So this initial compression is due to sample disturbance. So afterwards, we have a more or less elastic stage where there is a very somewhat stress-strain response. And as a strain is at this actual strain about 0.6, we can say that the stress-strain curve became nonlinear, distinctly nonlinear. Okay, so but still strain hardening. And then after the yield stress, the shales reach a peak. And after the peak, the samples experience very distinct post-peak strain softening behavior. So you can see that this is very brittle material because of the sudden strain softening and very pronounced strain softening. Let's plot two data, the Young's modulus and the peak shear strength. Young's modulus is plotted here in vertical axis for the different tests. And in the horizontal axis is the axial strain rate. As you can see, for each of the tests, for example, this one, they have three tests. We took the average, which is the red semicircle here. Okay, these are three tests again. We took the average of the test. And using linear, then we found that the Young's modulus more or less values power function of the axial strain rate. So it's a log-log relationship, actually. Similarly, for the stress deviator, or the maximum shear stress, also follows a power function with an exponent of 0.019 in terms of function. So you can see that both the Young's modulus and the peak shear strength are very much strain rate dependent, and the strain rate varies from about 5 × 10⁻⁶ to 1 × 10⁻⁻3. So it's a pretty wide strain rate. Okay, here are the samples after they were sheared. As you can see, the samples exhibited distinct shear fracturing because of the brittle nature. These are the traces of the fractures on both sides of the sample. Okay, but as you can see, the higher the strain rate is, as we increase the strain rate, the amount of fracturing actually increases. Okay, the amount of fracturing increases. The more fractures at higher strain rate than at lower strain rate. And if we plot the fracture lengths of the sample after loading, after they've been taken out of the loading cell, you can see that the fracture length increased by about 500 millimeter to about 850 millimeter. So it increases again with increasing strain rate. And the biggest change is between 1/10⁻⁵ and 1/10⁻⁴. Okay, in order to model this behavior, as you can see, the elastic modulus increases as a power function of the axial strain rate. So a very simple model is a viscoelastic model, which comprises of a static Young's modulus, E sub S, represented here by a spring, and parallel to that is a viscous damper, okay, which represents a strain rate dependent Young's modulus. So since it's parallel, this is just a sum of the two. So our Young's modulus is considered static plus strain rate dependent Young's modulus to the power of n. And you can see, using the data presented before, the experimental data can be fitted very reliably with this equation, with E sub V is equal to 25 gigapascal and E sub S is equal to 5 gigapascal. Okay, so it's a very good representation. Now let's talk about damage mechanics. Now, damage mechanics is an attempt to model the behavior of materials that undergo damage, particularly in this case, shear fracturing. So we can say we can start with an intact material. It may contain already some micro defects, okay? So, but during loading, the amount of defects in the material increases, okay? Here, the dots here, the dots here represent damage, okay? So we have two portions, an intact portion and a damaged portion. And we may have a completely damaged material and there's no intact material. So a measure of the amount of damage in the material are the relative areas of the intact and the damaged materials. In this case, the ratio of the damaged material over the area. So area being the load carrying capacity of the material. Okay, so again, intact, then we have partially damaged and totally damaged. So by equilibrium, the nominal stress multiplied by the total area should be equal to the intact, okay, intact material or undamaged material multiplied by the undamaged area plus the damage stress, okay, the stress that's carried by the damaged portion multiplied by the area of the damaged portion gives us the total stress. Okay, this is that one. All right, so that's simply from equilibrium, and again, the areas divided into intact and damaged portions. All right, so now we can represent the intact or undamaged material with a constitutive relation that is function of the elastic strain. The elastic strain multiplied by the constitutive matrix, elastic constitutive matrix, gives us the intact response. And sigma d is the residual stress. Damage again is now represented by the ratio of the area that is damaged divided by the total area. So this should range from 0 to 1. Okay? So if we divide both sides of equation 1 by the area, we should get the damage constitutive matrix multiplied by the elastic matrix, the residual damage stress divided by the damage parameter. So CD, the damage constitutive relation is just equal to 1 minus T times the intact relation. If you want, we can prescribe a residual stress, okay? A residual stress. So when D is equal 1, theoretically, the stress is 0 that the material can carry, but we can limit that. Instead of getting a 0 residual stress, we can make it a multiple of the peak stress. Okay, so that's the relation. So we take the rate form divided with time. So we get this stress strain relation. We have the damage rate multiplied by the intact constitutive relation times the elastic strain. The damage constitutive relation times the elastic strain, and the residual stress sigma d times the change in damage. Okay, damage distribution. How do we represent how much the volume of the damaged material in the material that is undergoing increasing defect? Well, we have to assume that the material already starts with some micro damage, okay, microscopic heterogeneities, and that the activation of these heterogeneities lead to fracture, activation, and growth. And fracture and the activation and growth are actually damaged. So it's reasonable to assume that these initial heterogeneities are statistically distributed, randomly distributed in the sample. Can relate damage to the length of the induced fracture, and in time, as shown a while ago, we can relate the fracture length to the axial shear strain, the amount of axial strain, rather, the total strain. So statistically, if the sample is randomly distributed, if the heterogeneities are initially randomly distributed, we can assume any statistical distribution, and it looks like the Weibull distribution is the best representation. So this is the probability of finding a quantity of epsilon E1 in the sample. Okay, epsilon 1 is the axial strain, epsilon 0 is the reference strain, and M is the so-called Weibull modulus, which will reflect the brittleness of the rock. We will show in the first model that damage accounts for nonlinearity, the deviation from the linear stress-strain relation, the nonlinearity in the stress-strain relation, shear failure, and strain softening. Okay. Okay, so fracturing here also may be considered as reducing the effective stress that carries the load. So at a given axial strain, between strains E1 and E1 plus D epsilon ln, the damage area is equal to AD is equal to the total area plus the probability of finding a certain length of fracture in the material. So integrating it from 0 to epsilon 1, we get AD is equal to A times this quantity, and finally we get the damage parameter AD over A is equal to 1 minus exponential epsilon 1 over epsilon 0 raised to the M. So epsilon 0 again is reference strain, and M is the Weibull modulus. Okay, let's do this for the total stress test that I just showed you, under interaction loading without regards on the pore pressure distribution. So relating again intact stress to total stress, intact stress minus the damage should be equal to the total stress. Hooke's law for the undamaged material with the primes, the materials are the primes, they're the intact or effective materials. are given by this, where sigma 1 is a function of Young's modulus epsilon 1 plus Poisson ratio and sigma 2 and sigma 3. Okay. Here, mu prime is the Poisson ratio of the intact material. Okay, and again, epsilon 1 is the intact strain. So we get this substituting back the equation 1 to equation 2, we get this relation. A very important assumption in damage mechanics is the so-called Lemaitre equivalence of nominal and effective stress. So both the intact and the total strain, the strains are equal and the same, which is a reasonable assumption. So epsilon 1 prime, the intact is equal to the total or the nominal, and the epsilon 3 prime is equal to the nominal epsilon 3. So intact is equal to nominal. So if we get that ratio, we can also show that the Poisson's ratio for the material for the intact and the nominal are both equal to 2. So apply the triaxial condition of sigma 2 is equal to sigma 3. We have this relationship where Q is the deviatoric stress or the shear stress, okay, which is independent of pore pressure. And C is equal to P2 mu minus 1. For android loading, we assume mu is equal to 0.5, and that's an incompressible material. Hence, C is equal to 2, and we have this relationship, stress-strain relationship, axial stress versus shear stress. And if we use our previous, the Young's modulus, we can bring it to this equation. Okay, so we have the static and the rate-dependent Young's modulus multiplied by 1 and minus D times E. And the result is unbelievably a very simple model. It's a one-dimensional model. So we have two equations for viscoelastic only without damage before yielding occurs, that is before the stress-strain relation become axial, epsilon 1 up to epsilon y, epsilon 1 y. We can consider epsilon 1 y as the yield strain. We have this very simple viscoelastic relation. Once we have exceeded the axial strain rate with damage stress, then this is the relationship. Still very simple, where Qy is the rate dependence deviatoric stress. So that is the yield stress for the deviatoric loading. Here it illustrates the effect of the parameters, two parameters, variable parameters on the shape of the stress strain curve. Again, the material starts to yield here, epsilon y and y or sigma sub y. This slope is equal to Young's modulus. This illustrates the effect of the Y-Bull modulus. As I said, it's a measure of the brittleness of the material. For this case, we use a reference strain epsilon sub 0 of 0.75. As you can see, as you increase M, so this is increasing M from 1 to 10, you can see that increasing M increases the shear strength. The material is stronger. Also, it shows a more distinct strain softening. So there is a more sudden drop in the shear stress towards a residual stress. The reference strain, this is for M is equal to 4. The reference strain also has a similar effect, increasing of epsilon sub O increases the shear stress, the peak value, this is the peak, and also the strain, the axial strain corresponding to the peak. So both the peak increases and also the stress strain curve move to the right before they drop and go to residual. Okay, so this is a comparison of model prediction versus experimental data for the long maxi shale that I showed you a while ago, the experimental results. These are for all the strain rates from 510 to the minus 6 to 110 to the minus 3. This is the shape. These are the individual results of the shear stress versus axial strain. This is axial strain rate of 1 times 10 to the minus 5, all the way to 110 to the minus 3. Okay, so you see the pit are remarkable. The pit are very good. Sometimes though the residual shear stress is slightly lower than the experimental data, but overall, I think this is satisfactory. Now let's move on. Okay. One of the things about the model you will notice is that I did not prescribe a shear failure criterion. Okay, I did not prescribe a shear failure criterion. I did not prescribe a shear failure criterion because it is an outcome of the damage formulation. Okay, so a shear failure criterion is not required. If we differentiate this stress-strain relation, the bottom one, Q versus E sub y, we differentiate it with respect to E sub 1, we get this derivative. And if we set this to 0, we get the actual strain rate at which the peak is going to occur. And the peak is the shear strength. Okay, so we can see that it is constant. The peak at maximum shear stress, Q max, is given by this function only of epsilon y, 1y, the reference strain, and the Weibull modulus. And if we put back this shear strain in this derivative, we get a very simple expression, this expression for the Q max, which is a function of C, which is again just a function of the constant model parameters, and the static and the strain rate dependent Young's modulus. Substituting all the values from this table, by the way, these are the parameters that are required. We only need 6 parameters to represent the model. Substituting it back, we get this stress-strain relation. These are the experimental points, and you can see the model prediction is excellent with an R squared of 0.99. So again, the failure was not predicted, was not necessary a priori. You don't need it at the start. It's just an outcome of the damage of the material. Okay, so the peak in the stress strain curve is properly predicted. Okay, I'm sorry, I keep on moving to this. Now let's talk. Let's expand the model for effective stress viscoelastic model for triaxial shear loading. So now we have a full triaxial loading, but also in terms of effective parameters. Effective means total stress minus pore pressure. Okay, so we use the Cambridge invariants, P and Q, and volumetric strain and shear strain. The elastic stress-strain relation is given by the elastic modulus 3G, and as before, that could be 3G, could be both, could be viscoelastic with a static component and a rate-dependent component. Okay, so before yielding, we have elastic. After yielding, when we reach Q sub y, then the damage occurs. In this case now, damage is a function of the shear strain, epsilon sub s. It's a function of shear strain. Okay. Now we need to formulate as well the volumetric change. The volumetric change is composed of 2 parts: the compression or consolidation volumetric strain and the dilation. Sorry. I don't know what's happening. Okay, and the dilative volumetric strain. So this is the compressive volumetric strain is equal to the change in the mean stress divided by the bulk modulus. And the deviatoric strain is as a result of the shear strain increment. We have here the shear stress ratio over P, and A times of C is equal to the slope of the phase transformation line at which the material changes from contractive to dilative response. So, okay, so when Q over P is less than N sub C, then this is a positive volume, which means it's compactive. But when Q sub P exceeds N sub C, then it is negative, means it's dilated. If we set dE sub B is equal to 0 and solve for dP, this is the change in the mean stress during undrained loading. Okay, we now have also the yield criterion, because here we only have QY. So the QY now is a linear function of the mean stress. So this is just a straight line function, a more column function. We also found that the bulk and the shear moduli are dependent on the mean stress according to the power function given here. So we have the bulk modulus increases as function or power function of A, and shear modulus also increases as power of P, okay, with exponent B, okay. So here's a comparison. We now have more parameters, 8 parameters, I believe, 1, 2, 3, 4, 5, 6, 7, 8 parameters that are needed. So this is compared with the results on peer shear by Islam and Scholar. Okay, these results were taken. Note that there are very few undrained shear strength, shear tests, triaxial shear tests, and shale with pore pressure measurements. It's very difficult. It takes a long time for the pore pressure to equilibrate between the sample. Okay, so these are very good results. You can see that the stress strain curves are well represented for different combining pressure, initial combining pressures, 10 megapascal to 20 megapascal. But more remarkably, you can see the very good fit of the effective stress paths in the PQ plane. Again, all are effective stresses. So case initially shows contraction, hits the zero dilation line or the phase transformation line, then starts to dilate. Then strain softens, so it elbows to the right and down a little bit. Okay, the yield surface is linear, as I showed a while ago. The zero dilation line is also straight line with zero cohesion. And the failure surface from the peak, I can show this to you. This can be predicted by the model as well. This peak's failure surface was not described a priori, which is linear. So again, like in the previous model for the total stress, shear failure criterion is not necessary. It comes out as a result of damage. I cannot derive a simple analytical model for the shear strength, but we can predict it numerically. This is the model predicted shear stress criteria, failure surface. This is the experimental. And here's a comparison of the experimental and the predicted failure surface. And again, the predictions of the failure surface are excellent, good predictions. Okay. Let's now go to the second model, which is viscoplastic. Why viscoplastic? Well, it is more rigorous than the viscoelastic model, and of course, more complicated as a result. The main thing is that if you add plasticity, then you can also account for inelastic or plastic deformation. You can easily more rigorously account for the residual shear strength response. And you can show this to be thermodynamically consistent. Here's the plasticity part of the model. We have a yield and failure surface, function of Q and P, and the damage parameter D. Okay, so we have 3 parameters, M, alpha, and K. Okay, they obtain as curve fitting parameters. So the failure surface is nonlinear. Okay, it's hyperbolic actually. Where P is the mean stress and Q is the shear stress. The hardening module, the hardening functions of are given here. You can see that alpha and K increases exponentially, or rather decreases exponentially with as function of the deviatoric plastic strain. Okay, the deviatoric plastic strain. We need a plastic potential. In this case, we assume it to be non-associative. And we use simply a von Mises type plastic potential with the main parameter beta. Beta is a measure of the dilative characteristics of the material. We have the flow rule. Okay, we have the flow rule here to get the plastic strain. Just take the gradient of the plastic potential with the terms of stress. We have the Karush-Kuhn-Tucker relationship, which says that the plastic multiplier should be equal to 0. The yield surface should be less than or equal to 1 or 0. And the product of the yield surface and the plastic multiplier should be equal to 0. Then we apply consistency condition that allows us to solve the plastic multiplier. Okay, damage. Damage is consisting of 2 competing components, a thermodynamic force y sub d, okay, which is a function of the volumetric strain. So now damage is a function of volumetric strain. In the first model, damage was a function of the axial strain. Second model, damage was a function of the shear strain. Now the damage is a function of the volumetric strain. Okay, so again, R sub O is equal to RD1 minus D. And we again use a damage formulation, which is the same, a Weibull distribution of the damage. Okay, and we come up with this damage rule. There is a beta here to control the amount of damage that we have. Okay, so if this is equal to 1, means you completely go to 0 in your residual stress. But if you have a number less than 1, then you can control the amount of residual damage that you can get, and also hence the residual shear stress. Let's talk about thermodynamic consistency. That's an important component of the model. The internal energy of the material is composed of the strain tensor epsilon, S the entropy, and some internal variables. If we get the rate of this, time rate of this, we could show that the rate of the change in the internal energy is equal to the product of the trace of the stress tensor and the elastic and the strain rate tensor minus the derivative with respect to the coordinates xi of the heat flow. Okay, so the work done by the stress multiplied by the strain rate is equal to the is countered by the change in the heat flow in the material. We apply Clausius-Duhem inequality for the non-violation of the second law of thermodynamics. So the rate of the entropy should be equal to the rate of the ratio of the heat flow and the temperature as a derivative of the coordinates. We can simplify this and it comes up to this. And the sum of all these components should be positive or equal to 0 to be consistent with the second law of thermodynamics. Okay, so we can split the above to the mechanical dissipation, that's the stress and strain dissipation, and the thermal dissipation. Okay, again, so this is the Clausius-Duhem equation, and I'm not going to go through that. We can also divide the total strain energy or our internal energy into an elastic and a plastic component. Okay, so the elastic is a function of the total and the plastic strain, and the plastic is just a function of the damage and then in some internal variable. The energy, the elastic energy is given by this, the damaged material multiplied by the elastic strain, which is the difference between total and plastic strain. We could show that the derivative of the strain energy with respect to the elastic strain gives us the stress, and that should be a product of the damage constitutive relation and the elastic strain. Okay, so at the end of the day, we derive this equation. So the rate of work of the material, the strain, the change in strain energy due to plastic deformation, and the change in strain energy due to the change in damage should be equal to the thermal dissipation. So this is the work done by the material due to plastic corroding. I'm sorry. And this is the work done by the material due to the change of damage. So we have two plasticity dissipation and damage dissipation. And we can neglect, since the sample is very small, very difficult to detect thermal changes, then we can just assume that temperature change is equal to 0. Okay, all right. These are the important things to note about the thermodynamic consistency of the material. We can see that the damage dissipation, which is a function of the damage force times the damage parameter, the rate of the damage parameter is always greater than 0, because the thermodynamic force is positive and the damage rate is negative. D is always increasing. The plasticity equation, this one, the product of the stress tensor, the trace of the trace of the stress tensor and the plastic strain rate is always non-negative for 3 conditions. We have an associative flow rule, a convex yield of failure surface, and use of normal flow rules. Okay, those are the three. Okay, so however, as is assumed in the model is non-associative, so we already violate this. So we have non-associative flow rule. So this product of the stress tensor and the gradient of the plastic potential can be negative. There's an instance to this one. So in this case, we cannot avoid negative dissipation. But this is the same as all other models out there with non-associative flow rules. Okay, all models with non-associative flow rules do not satisfy the thermodynamical law. Okay, so we can have plus-negative plastic deformation. What is the outcome of the, what is the impact of the negative energy dissipation for non-associative law is that we have constitutive relations that is non-positive definite. It's not positive definite. In fact, it's non-symmetrical because of the non-associative flow rule. Therefore, it has a zero or negative. It can have a zero or negative determinant and can produce negative eigenvalues. As a result of that, we can have bifurcation in stress strain curve, okay, and results in strain softening and strain localization. Okay, so for an associated flow rule, again, we can have negative plastic energy. The important thing here is that damage added to the plastic has a stabilizing effect because damage always produces positive energy dissipation. So it stabilizes any negative plastic energy dissipation from non-associative rule. We note here, okay, that although we have a non-associated flow rule, we are not invoking bifurcation or strain localization as the reason for the strain softening. Again, the strain softening is a result of the damage of material due to the initiation of the fracture and the propagation of the fracture during shearing. Here are some comparisons. We now have quite a bit of parameters. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we have about 15 parameters, 16 parameters. That's quite a lot. That is the disadvantage of this model. These are the yield and failure surfaces using a North Sea shale, test on North Sea shale, very brittle material. And here's a comparison of the predictions of the model versus the experimental results for 6 tests, okay, of different stress paths. These are different stress paths. Some are extensional, some are compressive, all of them are in drain. Some of them are with sigma parallel to the bedding plane or perpendicular to the bedding plane. In general, though, the trend is well represented. Okay, all right. So let me conclude. I have presented 2 models, viscoelastic and viscoplastic. Damage model for strain rate dependent shear behavior of shale. Both models use damage as represented by a Weibull distribution function based on an initially random distribution of heterogeneities in the shale to model damage by fracture initiation and growth. Okay, so increased fracture length means increase damage area or reduce load. In the very simple viscoelastic model, very simple actually, damage accounted for the nonlinear stress strain behavior, shear failure, and strain softening. Okay, all of them accounted for by the model. Failure surface was not needed. It's not necessary a priori, but it's simply a consequence of the damage. The viscoplastic model accounts for inelastic strain, unlike the viscoelastic model. And again, damage accounts for strain softening. The viscoplastic model was shown to be thermodynamically consistent, showing positive energy dissipation for associative flow and potentially negative energy dissipation for a non-associative flow, like all constitutive models out there with a non-associative flow rule. However, damage has a stabilizing effect and opposes the negative work that is done by the plastic deformation for non-associated flow. And I've shown several comparisons of the model predictions with the experimental data, and you can see that the fit with the three shales, Long, Maxi, Pier, and Norte shales, are satisfactorily predicted by the model. The models that they perform extremely well, I believe. So that's it. I'm not sure I will be able to answer questions since I won't be there, but I thank you very much for listening to my presentation. And I would like to thank particularly the organizers for giving me the opportunity to give this keynote lecture, which is a very big honor for me. I know that the Polish community have a very strong and reputed reputation in terms of mechanics. So this is indeed a big honor for me. And again, I apologize that I won't be able to be there because of my current health condition. Thank you very much. Goodbye.